All right, so in this video, guys, we are going to be discussing molecular orbital theory. Right? This is molecular orbital theory. Now, so molecular orbital theory is very different from what we've learned, which has been so far has been valence bond theory, right? So with valence bond theory, we talk about 1s orbitals overlapping with sp3 orbitals to form a bond, right? But this is not the case for molecular orbital theory. When it comes to molecular orbital theory, we can understand this by saying that the number of atomic orbitals that come together will equal the number of molecular orbitals, right? So atomic orbitals an atom has equal the number of molecular orbitals. So just like atoms come together to form molecules, atomic orbitals will come together to form molecular orbitals. So let's just give an example here, and let's just talk about an alkene such as this, and let's specifically talk about the pi bond, right? The p orbitals that overlap to form this orbital, right? So let's talk about this. All right, so if we look at that pi bond and we say, okay, well, what atomic orbitals come together to form that pi bond? Well, we would say, well, the atomic orbitals that come together to form that pi bond are the p orbitals. So if we draw this with respect to energy, so here's energy, we can say, okay, well, we have two p orbitals. So here's one right here, and here's another right here. So these are the atomic orbitals that make up that pi bond. Now, so these p orbitals can come together to form molecular orbitals. So if you remember, we said there are two p orbitals, so two atomic orbitals. So they're going to, how many molecular orbitals will we form? Two, right? Two atomic orbitals will equal two molecular orbitals. So if we look at this here, we'll have one possibility is that those p orbitals will come what we're very used to drawing is that they'll come together and overlap this way, right? And in this case, what we see here is that these are in phase, right? They overlap very nicely, and we can see that. We can designate it like this, right? This is what we would call a bonding orbital. This is what we'd call a bonding orbital, which we also call it the pi orbital, molecular orbital. And this is also what we call a constructive interaction because we're forming a bond, right? So if we have electrons here, one electron here, one electron here in those atomic orbitals, what can happen is that those electrons can come and be put into this molecular orbital. But just like these atomic orbitals can come together in a constructive fashion, they can also come together in a destructive fashion. What do I mean by this? Well, instead of them overlapping in the same phase, as we can see here, these would come together in opposite phases, so something like this. Right? So what I mean by that is that now these phases do not overlap. And there's a repulsion here, right? There's a repulsion here that keeps them from overlapping because they're not of the same phase. So we still have a molecular orbital here. So here's the energy. Here's a molecular orbital. But this is what we would call an antibonding orbital. Antibonding orbital. We also call it the pi star. Now this is also a destructive orbital. And this node here, which we draw with the dotted line, this indicates that there's no electron density. Well, that by a destructive orbital, that means if we were to put electrons into that orbital, it would cause a bond to break, right? Because it's destructive, and this is showing some repulsion. So this is the difference, right? You put electrons into a constructive orbital, you form a bond. You put electrons into an antibonding orbital or a destructive orbital, you end up breaking a bond. Now, with that said, there's also some other terminology that you need to be familiar with, and that is the term Homo and Lumo. So Lumo is this orbital right here. This is the lowest unoccupied molecular orbital. Lowest, oh, I'm sorry. Let me correct this. This is not the LUMO. This is what we call the HOMO, right? This is what we call the HOMO here. This is what we refer to as the highest occupied molecular orbital. The highest occupied molecular orbital. By that, what I mean is that it is the molecular orbital that is highest in energy that is occupied. So that orbital is the one that is highest in energy that actually has electrons in it. This one here is what we call the LUMO. This is the lowest unoccupied molecular orbital. This means that the molecular orbital that is lowest in energy, but that is unoccupied. That is what we refer to as the LUMO. All right. Now, so this was a very simple example, but you can imagine that we can get a lot more complex here the more atomic orbitals that come into play. So let's do a little bit more of a more complicated example, and let's look at the molecule benzene. So let's go ahead and do this here. So we're looking at the molecule benzene. Now when we look at benzene here, we see in this case that there are 6 p orbitals. So then we should have 6 molecular orbitals, right? There are 6 p orbitals, so we should have 6 molecular orbitals. So if we do this, the one that we can think of right off the bat that would be the lowest in energy is the one that we're familiar drawing here. Is where all the orbitals overlap nicely, right? So all the orbitals overlap nicely. So here we go. All right, there we go. So in this case, this is our lowest in energy orbital. So we can draw this out here. I'm going to use a little lighter green for this. Right? So there we go, our lowest energy level. Notice there are no nodes here, right? So no nodes in this lowest energy level, right? They all overlap perfectly. Now, every time we go up in an energy level, what you're going to imagine is that we're going to increase in the number of nodes. So a line in which there's not going to be any orbital overlap or 0 electron density. So if we look at this, then we can just imagine the benzene ring as a pizza that we're cutting in half, right, to get to 1 node. So here's an example of benzene with 1 node. So here are p orbitals. And in this case, what we see are that these orbitals overlap and these overlap, but there is a node that goes right between, right, which is showing that there's no overlap, that there is no overlap between these here, right? No overlap between those. So that's what we consider a node. So if we look at this again, then this would be another molecular orbital. Now, but just like we can cut the molecule vertical, we can also cut it horizontally, and we would get molecular orbitals that look like this, right? So in this case, these overlap nicely, and these overlap nicely, but there is a node that goes right between the axis here, right? Right between the axis. And if a node means 0 electron density, and an orbital means a probability of finding electron density, well, then we wouldn't draw the orbitals there because the node is going right through them, right? So we wouldn't draw them. So notice that these, the next energy level up, both of these have one node. And because they have one node, that would mean that they're the same energy, or what we call degenerate orbitals, right? They both have one node, so they would be the same energy, or what we would call degenerate orbitals. So if we go up one more energy level, then you can probably predict which ones here are going to be, or how many nodes the next energy level will have. And hopefully you realize, well, if we're going up one, probably the next one will have two nodes. So if we look at this, we can draw them out again. So you just have to draw the core structure again, and then just to realize that it's just like a pizza, right? We're just going to try to cut it as evenly as we possibly can, right? As evenly as we possibly can to get our nodes here. So in this case, you can imagine that we could cut it, if I had to, cut it 1, 2, right? So if we draw out our p orbitals here, there'd be a p orbital here, p orbital here, here, and here. So that would mean that these would not overlap, neither with these two from top and bottom, these would not overlap. And of course, from side to side, they would not overlap, right? So there's no overlap right there. And then again, this would be another molecular orbital. All right, one more time. So we can draw another one here. Right? And in this case, what you can imagine is kind of a little bit more like this. Where this orbital is not going to overlap with these, but these will overlap with each other, and then this will not overlap here. So we see a node right here, and we see a node right here, right? So that would be another molecular orbital. And if we look at that, then that means that both of these have two nodes, which would again be degenerate, which means equal in energy here. Now you can imagine, so we said we had to have, since we have 6 p orbitals, right? So we had 6 p orbitals to make up the pi framework, then we should have 6 molecular orbitals, right? Molecular orbitals here. So we already have 5. The last one would most likely be the one that's highest in energy. And if we're going up another energy level, you can imagine that this one's going to have 3 nodes. But since it's the one that's highest in energy, you can also imagine that none of these nodes, none of them are going to overlap at all, right? So none of these p orbitals are going to overlap at all. They're all going to be in opposite phases of each other. So we can imagine that this one here is going to be down, up, down, up, down, up, right? So none of these overlap. We can see that there is a node right here. 1, 2, 3, right? So this would have 3 nodes here. So that's basically how you can draw these out. This is going to require some practice, no doubt, but not something that you can't master. Now, with that said, if we look at this and we start to fill the electrons, right? And we say, okay, well, how many pi electrons does benzene have? Well, benzene has 6 pi electrons. So we follow what we've always been taught. You want to put electrons into the lowest energy level first, and then you also want to make sure that you put them opposite spins. Then we would say this is 1, 2, 3, 4, 5, 6. So there are our electrons here. So with that said, what we can see here, and I'm going to go ahead and erase this part over here just to draw some space. These orbitals, these 3 orbitals right here, are what we would call the bonding orbitals, right? There are electrons in them, so these would be the ones contributing to bonding. These 3 up here would be called the anti-bonding orbitals, right? The anti-bonding orbitals. These are the ones that don't have any electrons in them, but if we were to put electrons into them, then we'd end up breaking bonds, right? We would end up breaking bonds here. So with that said, let's see if you can determine which orbitals here, or how about this? Let's just do a question here. How many nodes is the HOMO going to have for benzene? Looking at this diagram here, how many nodes is the HOMO going to have for benzene? All right, so go ahead and pause the video, think about that, and then go ahead and answer the question. All right, so hopefully you're able to answer this question and you realize that HOMO means highest occupied molecular orbital, right? Highest occupied molecular orbital, which means that these two right here would be the HOMOs, right? These two would be the HOMOs because they're the highest in energy that are occupied, right? The highest in energy that are occupied. Now go ahead and pause the video and tell me how many nodes would the LUMO have? How many nodes would the LUMO have? Go ahead and pause the video. All right, so hopefully you figured this out and you realize that the LUMO in this case is going to be these right here. Those are the lowest molecular orbitals that are, so the LUMOs are going to have two nodes here, and they're the ones that are the lowest in energy that are unoccupied, right? The molecular orbitals that are lowest in energy and unoccupied. So hopefully that makes sense with you and gives a little bit more understanding. So a few key things to take home from this is that as we increase in energy, notice that the number of nodes also increases. We go from 0 nodes, next energy level up 1 node, next energy level 2 nodes, and then the ultimate one here 3 nodes. So we need to keep that in mind, right? Um, so, but you might ask yourself, well, Dr. Elad, you kind of went through this with us. You said there's one orbital that has 0 nodes, 2 that have 1 node, another 2 that have 2 nodes, and then one last one that has 3 nodes. How would I know that? How would I figure that out? Well, you can do what we call is drawing a frost circle, right? So I'll show you how you can draw a frost circle to determine this. Now, frost circles are not the same as molecular orbitals. Frost circles just help you determine the relative energies, but they're not the molecular orbitals. These are the molecular orbitals because we actually see the orbitals, the balloon structure type things, but the frost circle will just tell relative energies. Your book calls it, I think it calls it a polygon inscribed method. I call it a frost circle. That's what I was taught. So with that said, all you really have to do to figure out those relative energies is to draw a circle and then put the core structure of that circle, of the molecule that you're trying to figure out, into the circle. But you want to make sure that one of the vertices is pointing straight down. So what do I mean by that? Well, if I draw a benzene ring into this circle, here's my benzene ring, right? I want to make sure that one of the vertices is pointing towards the bottom, right? One of the vertices is pointing towards the bottom. And then every time that it hits an outer part of the circle, that is a molecular orbital. So it hits here, here's 1, right? It also hits here, 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 and here. So that would be another orbital, another orbital, another orbital, another orbital, another orbital. So this helps us understand the relative energies of those orbitals. That'd be 1, 2, 2, 1 going up. We can put the electrons into each one. 1, 2, 3, 4, 5, 6, right? And then we can clearly see that these here would be the anti-bonding orbitals, and these would be the bonding orbitals, or at least bonding energy levels, right? The orbitals, again, are the ones with the actual drawings. These are just showing us energy levels. But that's how we were able to figure this out, right? This is how we're able to figure this out. Now, a frost circle can help you understand aromaticity also by looking at the HOMO of the molecule. Because ultimately, if HOMOs are filled here, then this suggests that the molecule is aromatic. Right? If the HOMO is filled, it suggests that it's aromatic. And we see that these HOMOs are completely filled, so they would be aromatic. All right, so for practice, if you want some extra practice, how about this? Take this molecule. Here's this molecule. Draw me a frost circle. Then draw me all of the molecular orbitals and indicate which molecular orbitals are the HOMOs and which are the LUMOs. Okay? So again, draw the frost circle to get the relative energies, then draw the molecular orbitals and indicate which ones are the HOMOs and which ones are the LUMOs. And if you think you get that, then you can always take a picture and send it to me, and we can see how you did. All right. Hopefully this clarified molecular orbitals for you, and until next time.